Episode 3 of the World of FPGA Podcast. Let's discuss today the differences between development of electronics, software, and firmware for FPGAs. Welcome to the World of FPGA Podcast. I'm your host, David Kirchner, and I will lead you through the world of FPGA. And now, let's begin. In today's episode, I would like to discuss a topic which I think is important if you want to understand what is FPGA development. I would like to talk about electronics, about software, and about FPGAs. But first, let's clarify some terms. I have 3 points which I would like to categorize the following comparison later in this podcast. And the 3 terms, the first is flexibility. So with flexibility, I mean how flexible is a system when we have changes in our development stages. Flexibility means also the possibility of adjustments and what is about a platform. So the thought, the idea to create a platform. How flexible is this system? The second term is know-how. Which knowledge is necessary for the point I talk about? So one of the 3. And how can we learn the basic knowledge of this main point? Then the question is, how can we continue our education? So what can we do after basic knowledge? Is there the possible to learn more? And yes, learning by doing, this always helps and just works. But in my opinion, it is better to have a training on the point, not only just have always learning by doing or just going from seminar to seminar. So the last term is complexity. So how easy is it to manage such a development project, and what is with maintainability? So if we have changes later on, how can we bring them on the street or to bring them out in the world? Okay, we have 3 main topics. So electronic software and FPGAs with all the 3 under points, and I would like to start with electronics, or more or less hardware development. Under the point flexibility, we can summarize the following thoughts, the following ideas. So it is at the beginning of a project, we are very flexible in a hardware development. But if we think further, the needed requirements of a system must be set at the point of the beginning of a project. So we have very much work in our concept phase. We have to write down our ideas, discuss this, and more or less have everyone in this concept phase together to find all requirements the system needs, because later changes, or the later the changes are coming, it is more complex to implement these changes. If you think you have you've done your schematics and you are in the end of the layout phase, and then comes an idea, well, sometimes you have to rip up all the hardware again and doing a new design. For example, the size changes or the outline of the PCB changes or something like that. So we have to plan flexibility in front of our development. We cannot change our system if it is released. So changes after a release are more or less you need here a redesign and new prototypes and a high level of testing that everything else also works as you have planned it at the beginning of the project. So what know-how is needed for electronics or for hardware development? And I see here two ways. The one way is you have an electronics technician training. So you normally in German these are 3 years or 2.5 years, 3 years, just roundabout, and then you have a basic qualification for electronic development. But it is more common that you are studying electrical engineering and then you get a specialist in one area, maybe in medical systems, medical electronic, or in avionic, or in what do we have? Telecommunication, and so on. So you can get a specialist in one of this area. Later on, you can also do some advanced trainings in different areas of electronics, and then you can learn some special things. Yeah, and the complexity with good documents, you have a good overview and you can handle all the complexity of such a system. The emphasis lies on good documents. That's more or less a problem to have good documents. Sometimes you see a schematic and it is lines with only labels and blocks with only some short strips and then a label with a cryptical name. That's not so a good design style. In the most cases, hierarchical blocks make sense. In the most cases, or more or less in every schematic you create, it is a good idea to have a top view of your system and then go deeper into the single blocks in your design. And it's always a good idea to have on all pages the same signal flow direction. So you start, for example, on the left side of your paper with the inputs, or it's a connection from a slave to a master. That's more or less also on the left side. And on the right side, you have the outputs, or if it is a master, there you have on the right side the connections to the slaves for bidirectional interfaces, for example. And also the power flow, you can, on the one hand, use global power supply nets, or you use the up to down direction for the current flow or for the voltage. Most time on the bottom of a block you have the ground connections. And if you have modular constructions, this would also help to reuse types of your, to reuse parts of your development for new development system, for developing new systems. So that's what I say. Okay, this is electronics. With the 3 sub points, now we go a step further to software. In software, we look now into the flexibility, and software is very flexible. The development can start in parallel when hardware development started. It can start later in the development phase, and changes can be easily rolled out into an existing hardware systems, for example, with a software update. And you can test many functions automatically, so you can use programs to test your software. If it's communicate with other systems, you can simulate them, and so the flexibility is very high, and you can change easily your requirements and later doing the development of the software. On the know-how side, software development can be learned with a software development training, or you're studying computer science. That's the other way in the university or in the University of Applied Science, for example. And there are always some advanced trainings in different areas of electronics. These are the three ideas about know-how in the area of software. And the last point is complexity, and software is high complex. It has a very high complexity, and therefore there's a high demand on a clean structured source code. The source code must be easy to understand, easy to read, easy to change. That's my idea. And also the coding style should be agreed with all other developers in your team. If everybody has another kind of coding style, then it's not so easy just to transfer code from one person to another person because they didn't understand it. And one very important point is comments are always required. So always write some comments in your source code, at least at the beginning of a function. And in the coding style, often it's good to have a point that variable names should be not only single characters or single characters with numbers. They should have a good readable name and understandable name. And now we came to the third main part, the FPGAs. And we start again with flexibility. And the first thing is the hardware around an FPGA. Have I described some minutes ago in the blog of hardware development. So I will not repeat these points, but one important thing here is when you are working with FPGAs, you can use the pins of an FPGA in different ways. Just as an example, if you have a connector which is connected to the FPGA, you can implement various functions later in the development. So the hardware can be fixed and can be created and build a prototype and so on. And later you can decide, oh, and that pin here, this is my serial input, and this is my serial output, and this is my LED, and this is my, and so on. I think you know what I mean. It is flexible if you have rooted out maybe the open pins, the not used pins of an FPGA to a connector. And the function of the connector is determined later by configuration. So if you load your configuration into the FPGA, then the function of the pin will be set. And this brings us to the idea about a platform. You can create with FPGAs easily platforms. You have the same hardware for different functions, for different products, for different systems. Because the function of such a platform will also be later put into the system by configuration, not by design of the hardware. If you have a good platform concept, this is important because if you're missing some pins or pins are different connected, then you're lost. You have to do two hardware systems. The next point here is know-how. And studies, in, for example, electrical engineering, most time you only get a little overview over FPGA development. Own courses on FPGA development on university, I haven't found. I think most is done in technical computer science, for example. So if you want to study and want to dive deep into FPGA development, go in the direction of technical computer science, there is some things of FPGA development, maybe in projects and so on, and later do some special technician trainings. And I think this is something that is a good way to have a basic understanding through the university, for example, with technical computer science or electrical engineering, and later on get a specialist with adequate technical trainings. Later on, there are also advanced trainings. There are many advanced trainings, and yes, you can always do self-learning or try and error. I've talked about this in my about my past, but this is a long road with many pitfalls. And but on this point, my platform World of FPGA can help you with this with many courses. And just stay tuned for this. We start on Pi Day 2023, so it's the 4th of March 2023. So this is a short advertisement block here. Now it ends. So, and the last point here is complexity. This is, I would rate this as quite highly, because if you have an FPGA with many cells and with many things to do, we have many description files for the FPGA functions. There are some tools with graphical methods, for example, block designs, that helps a little bit and can show the flow of the signal through the FPGA. But in a complex design, you have many blocks with many connection lines in between, so it gets more and more difficult to see the correct signal flow. Some tools provide hierarchy designs, and you can put some blocks together into one block, and then you have a more or less good overview over the signal flow through these blocks, and then you can dive into other blocks and doing, for example, changes there. And important, similar to software development, is you should have a coding style fixed in front of the development, just to have the same signal. The signal styles, name styles for inputs, outputs, constants, signals, and so on. And always use comments in your, for example, VHDL source code, because if you have no comments on your own, you will not understand your code in half a year. So sometimes this was my problem. I have written some very good stuff, and later on it wasn't possible for me to understand what I've created and have to do re-engineering on my own software. Yeah, that's now the question, what is an FPGA? Is it hardware or is it software? On the one hand, an FPGA is hardware, because it's a semiconductor. We can pick it up with our fingers and look at it, so it's a physical thing. It is hardware. It's a structure of logical cells and of registers, and it has inputs and outputs and power supply and such a thing. But an FPGA without configuration is completely useless. This FPGA can do nothing without configuration. So it's, on the other hand, it's also software, because we have software-generated configurations for this FPGA. Yeah, no programs are running in this FPGA. I've talked about it 2 episodes ago. You are describing the the behavior of the system. You have no program running, except you have a processor IP core in your FPGA. In other words, an FPGA is a software configurable hardware. It couldn't be more complicated than that. So it's a mixed up of both worlds. And that's the funny thing, the interesting thing of FPGAs. I think you can build much more comparison matrices, but I think this is enough for today. Or now it's your turn. Have I forgotten something from your point of view? Well, just write me in LinkedIn. There you find this episode after it has released in the podcast, in the podcast stream. You find further information on the website, in the show notes, and the show notes you can find at world-of-fpga.com/WFP003. If you found this episode helpful, please rate it on Apple Podcasts and share it with your colleagues and friends. That's the end of today's podcast episode. Thank you for listening and for your attention. So I say goodbye here next time, your David Kirchner.